Yeah, thanks for the introduction. Hi, Mars. Yeah, it's very nice to be back, and it's also very nice to be back to giving the QSOF seminar. I think the last time I gave one was using like half, like fill in the blanks iPad slides remotely in 2020, if I remember correctly. So this is much nicer. Yeah, I want to talk about permutation superposition oracles, and yeah, we use them for at least at this point still for very simple quantum gray lower bounds, but you will see. So let me get started. Here's an outline. I will start by talking about the compressed oracle technique or the superposition oracle technique, because I want to begin by describing a little bit what the challenges are to get an analog, an analogous tool for random permutations instead of random functions. So then I will describe these challenges and the key ingredient that we use to at least partially tackle these challenges, which is the strictly monotone decomposition of a permutation. And then I will describe the oracle and a little bit about the techniques. So let's start by looking at lazy sampling. So this is like very basic stuff, so I will probably go quickly. So if you have a random function h that maps n bits to n bits, let's say for simplicity, then you can look at basically algorithms relative to an oracle for this function. And lazy sampling is the technique of statefully simulating such an oracle by basically not sampling the unused outputs, right? So in other words, basically whenever a query comes in that has not been queried before, we sample the random output and reply with it.
So what does mean stateful?
Stateful means the oracle keeps a like it has memory, right? It has memory. Like between two queries, it needs to remember the previously sampled outputs, so that if the same query comes again, the same input, then it needs to reply with the same output. At least that's the most general setting. In the classical setting, it's one convenient thing is that you can in principle assume that no repeated queries are made, then it's not stateful. But so this we replace this oracle by a lazy sampling oracle, and what does it do? It initializes the list. At least this like most general case, and that's also kind of more similar to the quantum setting. That's empty. And whenever a query is input, then we reply with an existing output in the list. And if that doesn't exist, we sample a fresh output and add it to the list and use it. So here's another point of view on this technique that turns out to be more useful for the quantum setting. So the outputs of a random function are independent and uniform. Uniformly random. So somehow there's no need to sample and store unqueried output. We can just use like a special symbol for to mean this output has not been sampled yet. Let's use this bottom symbol. So basically now we have like this huge list. It has mostly bottoms and a couple of sampled outputs. And that's of course inefficient because we don't need to store all these bottom symbols. Instead, we can use a sparse representation. And then in this example here, we just get the list that has pairs xy and x prime y prime instead of this huge list where somewhere in the middle there's like a y and a y prime. And the good thing is not only is the sparse representation efficient as a representation in terms of memory, but we can also use it, we can update it, right? Like instead of going back to the big representation, update it and then go to small again, we can efficiently update it directly. And this turns out to be the right picture for looking at the quantum version. Now let's make it quantum. So we have the quantum accessible random oracle model, which is basically just saying we're looking at algorithms that are provided with a quantum oracle for a random function. And this is the oracle unitary. It's the usual quantum unitary for a function. And so now we look at algorithms that interact with that unitary. And let's now look at this. This is the old slide where I described the classical, this alternative look on the classical random function oracle. or lazy sampling oracle. And now let's make it quantum step by step. So first of all, let's use the QROM, of course. The outputs are independent and uniform, but instead of sampling them and using XOR, we instead prepare a superposition of outputs and use CNOT to to replace the XOR into the adversary or the algorithm's register. And that's equivalent because we only ever use controlled unitaries to read out the superposition. So whether the computational basis measurement commutes with that operation. So we could measure immediately, and then we're back to the usual setting where we sample it. And yeah.
What superposition are you talking about here?
Basically, like whenever now let's think about basically the uniformly random output I need to reply to a certain input. Instead of sampling a uniform random variable, I prepare a uniform superposition.
So the value of hx is in uniform superposition.
That's right. Yeah.
So basically, you become entangled with this oracle.
Yeah, that necessarily happens. And now instead, yeah, we make everything quantum. In particular, we kind of make the dummy state. That means unsampled, or in this case, unprepared. We make it quantum as well. And now instead of this, before we were thinking like, instead of sampling it, we put this bottom symbol there. And now we can represent this by a basis change operator that just replaces the uniform superposition, which represents a readily sampled output by this bottom symbol, and vice versa.
Why also vice versa?
That's just to make it unitary. Yeah. In some minimal way somehow. Yeah. Now basically the internal state of our oracle now is a superposition of these states that are mostly bottom states and otherwise has some computational basis. Sorry, not some other states that are orthogonal to the bottom to the bottom state and to the uniform superposition. So basically, now it looks very similar to the classical setting, except that it's quantum. And for this talk, let's just not talk about the sparse representation. Now we have some quantum analog of the of this kind of sparse, or like this unsampled, or this partial function view, let's say, of lazy sampling.
Sorry, I don't understand. So this y tilde, is that supposed to be like a bit string? Because you say it's orthogonal to the all plus state.
It's a quantum state, and it has these properties. It's almost equal to, it's kind of the minimal. It's basically, you can think of taking the computational basis state y, and then doing like 1 Gram-Schmidt step with the uniform superposition. So it's like almost equal to the computational basis state, but orthogonal to the uniform superposition. So yeah.
Is it orthogonal or orthogonal? How can something be exactly orthogonal to? How can a basis state be exactly orthogonal?
No, it's not a basis state. It's not a uniform. Sorry, it's not a computational basis state. It is some other state that's orthogonal to the uniform superposition. But it's among these states, like in their subspace, it's the closest one to the computational basis state y.
Oh.
Yeah, that was still. I mean, of course, I can decompose my internal state into any basis or spanning set, but this turns out to be a useful one.
It's just sort of a small comment, right? When you say it's a superposition of states like this, I mean, that's not fully correct because it's not a pure state, right? Because it's actually entangled, as Maurice pointed out. So it's sort of, if you sort of just look at the internal state, you get a mixed state, which is supported by states of this form.
That is true. Like right. Basically, what I was thinking of, I was actually thinking of the global state. That's like the joint state of the oracle and the algorithm, and then it's a superposition that on the oracle side is spanned by these.
Yes.
Yeah. And maybe I'm going to ask you to take a step back because I'm a bit confused. Previously, when you wrote this y tilde there, it was the output of this H function, right?
Yes, and now basically, it is in some sense the best available approximation of the output of this H function if we just want to look at the internal register of the oracle.
And you need to have, the oracle has an internal register because it's stateful, so you need to have some quantum state inside it.
Yeah, and that's how we design it because that internal register turns out to be very useful.
So how should I intuitively interpret this internal state? Because it doesn't just say I recomputed H of X and I'm storing the result, right? What does it mean?
In some sense, that's exactly what you do, because if some query would be made on 0, corresponding to this very first register here, then this bottom thing would be replaced by the uniform superposition, which is like the equivalent to sampling the corresponding output. And then C naught is used to answer the query. And afterwards, the replacement unitary is applied one more time. So if somehow the output was not used, then it's returned to the bottom state.
So if the output was used, then this output will be stored in this internal state.
Oh, okay. If it's okay, I'd like to move on so that we can get to the permutation part. So I just wanted to quickly give kind of a description of the function, like the stateful simulation oracle for a random function that we have now. It initializes this register that's where all subregisters are in the bottom state, and on every query, controlled on the query input register being equal to the computation basis state X, it will basically convert the DX register into the natural representation, which is basically this uniform superposition. It will apply C naught to answer the query, and then it will undo the basis state change. And this oracle has been turned out to be extremely useful for all kinds of stuff. So up here is like kind of a cartoon of how to prove query lower bounds with it, because now we have this this internal register that kind of gives an indication what outputs are known to the algorithm and what are not. So the ones that are in the bottom state that represents kind of an output that's still independent from the algorithm's view. So we can kind of design projectors on this internal register that serve as a progress measure for query. And then one gets like this type of circuit here, and one can make an easy is maybe saying much, but a very nice upper bound by only looking at basically the operator norm of this oracle unitary turning a database that doesn't fulfill a certain predicate into one that does. And this was used for
when you talk about query complexity here, this is specifically query complexity with a uniformly random input, right? It's not the usual worst case query complexity.
That's right. Yeah, it's uniformly it's basically complexity of certain tasks relative to a random function oracle.
And what do you require from the algorithm solving a problem? Should it work on every input? Should it work on most inputs? Like what type of algorithms are you considering now?
It's like the thing that's relevant for cryptography is for randomly sampling the function, we need to characterize the success probability. So that includes basically, yeah, that's the expected success probability over the choice of the function.
It's okay if your algorithm fails on a few inputs.
Definitely. Yeah.
I mean, by input, you mean function?
What he calls capital H.
Yeah. In query complexity, what we call an oracle is called an input.
Oh, okay, cool, thanks.
And because you're computing a property of H, so I'm thinking of H as the
Yes,
input to the
yes,
algorithm.
makes sense, yes.
Usually we want to prove that the algorithm actually fails on almost all inputs. Only
Yeah, success probability equals half or something. That's if you're deciding on it.
yeah, or if it's like a long output, maybe even like a success probability negligence.
Right, so here's just a list of a couple of nice things that were possible to do with this, including analyzing some cryptographic constructions, but also including some kind of more fundamental results like for example, bounding the success probability when trying to find a multi-collision in a random function. Now let's try to dig a little bit. What are the core properties of this compressed oracle that make it useful for query logons? So here's basically a list of crucial properties, and they seem kind of maybe obvious or trivial, but I think they are essential for the usefulness. And it's basically that we have this collection of small independent random variables, and learning one of them, learning one output only requires looking at one of the random variables. Also, each variable only stores information about one output. So there's a one-to-one relationship between the random variables and the output, because the random variables are the outputs, right? So now in the compressed oracle, the usefulness of these properties stems from the fact that we can look at this one register to determine whether the corresponding output has been learned by the algorithm. Or we can look at the entire register and, for example, check, is there any output there? And remember that an output is basically something that's not bottom, right? So that's by definition something that the algorithm has learned. Is there any output that's zero, right? And that basically will enable us to for example, reprove a bound for Grover search for a preimage of 0. Right. So let's look at some properties of the pre-compressed oracle that follow from these. Now I call the oracle pre-compressed because it's not actually efficiently represented. It has all these bottom symbols, but it's just more convenient to look at. So here's the pre-compressed oracle and some algorithm interacting with it. So one thing that we can do now is we can just let the algorithm finish, then take this internal register and measure it, and then we get this string, which basically represents it. We can take it to represent a partial function. Some outputs are bottom, are undefined, and some outputs are some y's. Now the interpretation is basically, if the output is bottom, then the algorithm has not learned anything about it. And if the output is equal to some string, then the interpretation is the algorithm has actually queried that input, and except with negligible probability, it learned the same output that we have recovered by measuring this internal state. And that's where the usefulness of this oracle simulation comes from for query logons. Now let's look at the permutation setting. Let's try to repeat the success. I mean, it was very successful, this technique. And let's try to do the same. Here we're looking at the setting where we have a random permutation now, and let's stick to the setting where the input space is n bits. So we have some element pi from the permutation group on 2 to the n elements. The question is, of course, can we find a representation of this permutation that has the nice 3 properties that we collected? Basically, a collection of small independent random variables. Learning one output requires only looking at one of the variables, and vice versa. And obviously, that's not possible, right? Because the outputs are not independent. We cannot fulfill all 3 of these properties. We need to relax at least one of these requirements. So the first and maybe most obvious idea is to give up on the independence, because how convenient would it be to stick to the representation that just has a list of outputs, right? So then we have like small variables, look, they all represent the outputs and so on, but they are not independent. That is an idea that works in the classical setting, right? The classical lazy sampling of the permutation works exactly like that. If we have only few queries, then we have a list where the random variables that represent their outputs are almost independent. And there were attempts made in this direction, including by myself and co-authors, but basically they failed. Yeah, and the devil is in the inverse access to the permutation. Usually we want to provide an oracle for the permutation and its inverse. And for one-way access only, this approach actually works. There's basically we can switch to the random function view up to a collision bound. That's what Akinori Hosuyamada did for some cryptography proof. And then we are back to the function case, which is nice. But for inverse access, doesn't seem to work. So now the other attempt is give up on locality, right? Basically, we can of course represent a random permutation by independent random variables. For example, just use some way to specify it in terms of basically take some algorithm that takes as input a random tape and outputs a random permutation. Now the input is like a representation of that permutation, and it's a string of random bits. But of course, that will not have useful properties. So we want to like find a representation as independent random variables where that still have a meaningful, that carry kind of meaningful information, hopefully with relaxed locality also. So I just said that, and it's only useful if there's some locality. And one result that did that was by collaborators and myself, where we did find a collection of very small independent random variables that is has also nice locality. So each variable only concerns 2 outputs, but actually they don't fully specify the permutation. There's also some monolithic remainder, some mess that we kind of gave up on utilizing for the technique. And this was kind of fine for decision problems, but for search problems, it's not good enough. Yeah, so we were basically able to prove security of a construction that's called tweakable Evan-Mansour with exactly such an approach. Okay, so now after this kind of longish ramp up, let me come to the key ingredient for our construction. Okay. So the key ingredient to the construction is something called the strictly monotone decomposition of a permutation. So let's have a look at what that is. We have some permutation. Now, for convenience, I'm switching to capital N instead of 2 to the n. And forget about the fact that it's a power 2 of 2 because it doesn't matter for this discussion. And one observation is that we can isolate the value that this permutation has on input n, for example. So we can write the permutation as the transposition that just swaps n and pi of n times some permutation pi prime, which now is an element of Sn minus 1. It just permutes the numbers from 1 to n minus 1. Just going to stop for a second for you to process this. So that's nice. Right now we have kind of a recipe of how to split up a permutation that we can apply iteratively. And then we get a particular decomposition. Yeah.
Sorry, maybe I'm missing something. So you were saying I can always be understood as mapping n to something else and to something else back to n.
So this here is kind of composition of permutations. So for example, on input n, we know that pi prime it doesn't act on n. So here we understand pi prime as an element, still as an element of Sn, I guess, but it only permutes the elements 1 to n minus 1, and it has n as a fixed point.
But assume that for the original pi simply swaps and
That's what
another
I'm-
element.
but
That's one picture, it is obvious
Yeah.
in the picture.
So, right, if we have the input that's like n, and then we have like the other ones. And now we have
Just draw some random permutation.
But my point is, in general, a permutation doesn't have to swap n and some other number. It could
True.
make n
But
to
what-
7, but 7 does not go to n, but to 3.
Indeed, and the point is n goes to 7 here, but 7 does not go back to n, right? It first goes through pi prime and ends up somewhere here, maybe,
Okay.
and then that's the output.
You should do it for the permutation, there's a bunch of wires that are being exchanged. Well, you just put the n's wire back. That's what you.
I'm not sure I understand that, but maybe this picture is
Okay,
also
I get the
sufficient.
point now, yes, yes.
Good, so now we have this decomposition of pi into n transpositions. Some of them might be the identity. And they have a very nice structure, right? Like we have these t values here. It's only Tn that has an interpretation as an actual output of pi. But they, like the Tx is in the range 1 to x, right? Because we iteratively applied this decomposition. Now, that's great, but what happens if we input like a random permutation? The nice thing is that the value pi of n is independent of pi prime. That should be also somewhat obvious by this picture here, right? Like we know that pi of n is uniformly random, and basically now what's left to specify is kind of a map from the values 1 to n minus 1 that is injective and maps to the values like everything but pi of n, right? And that's still uniformly random among the set of these maps. So in the end, we get like this nice representation of pi as these t values, t1 up to tn, and they are actually independent random variables.
Is it a
And
unique
uniform.
representation of permutation?
Given the ordering we chose to apply it in, it's unique.
What does it mean? The ordering?
You know, we started with n, with the largest input, and then we went downwards. We could have started with 1 or in any other order,
Okay.
but if we fix the order, then this representation is unique. Yeah. So that's great. We found like hopefully a representation of the permutation as independent random variables that has nicer properties than an arbitrary one, hopefully. So let's look at the properties of this. By the way, this insight that these values are uniformly random in their respective ranges and independent, that's sometimes called, or the resulting algorithm of sampling a random permutation or applying a random permutation is called the Fisher-Yates shuffle. So it's not a new idea to look at this particular representation of a permutation for random permutations.
Is there some implicit renaming of the last n minus 1 elements after you've assigned where n gets mapped?
No.
Because pi n is probably in the range 1 up to n minus 1, and you don't want to create collision.
I mean, this is here a product of permutations, right? So I can definitely not create any collision.
N gets mapped pi n, right? And then the pi prime parts, it's possible that pi n lies in the range 1 up to n minus 1.
Yes.
The pi prime part starts to shuffle the numbers 1 up to n minus 1.
Yes. So basically, pi prime decides the value pi of Tn, right?
Mhm.
For example, or if, for example, definitely maybe we should look at pi to the minus 1 of n, right? Pi to the minus 1 of n, then I apply pi to the minus 1 to n. Like first n gets swapped with Tn, but then afterwards the whole of pi prime is applied. So basically, the only like if n was a fixed point of pi, then Tn needed to be n, right? But given that it's not a fixed point, then pi prime decides kind of pi to the minus 1 of n.
Might help to put this transposition on the other side of the equation. That then basically you have like this n by n times pi, and then you want to make sure that that is in Sn minus.
Yeah. So fine, we have this collection of independent random variables. Let's take a look at locality. So basically, in how far is this representation local in the sense that maybe I only need to look at few of these values to compute the permutation on a particular input. Unfortunately, it's not local. So as you probably have guessed by now, to compute pi of x, we need to look at all values px prime for x prime larger or equal x. It should be larger or equal. So that's not great. But luckily, actually, in a certain particular sense, pi of x only depends weakly on all but order the logarithmic amount of values of tx. So let me be more precise of what I mean by that. We make a definition. We say for a permutation pi in Sn with a given strictly monotone decomposition, we say that the location x prime is active for the computation of, for pi on x, if changing the value tx prime to any other value changes pi of x. So that's for now, that's just a definition. And just to give away the usefulness of it, we have this lemma that says that the expected number of locations x prime that are active for pi on x for a random permutation is logarithmic in the domain size. Let's kind of get more intuition of what this means. First of all, yeah, if x prime is not active on then there exists exactly one value t, so that if you change tx prime to t, then the output value changes, but otherwise the change doesn't change. Let's have a look at this in pictures. So here, this kind of wire diagram of the strictly monotone decomposition of some permutation. So basically, these blue lines, they represent the transpositions. Let's have a look at some the computation on some inputs. So if we input like the input 2 here, or 3, sorry, the input 3, then the location 3 is definitely active. But here it turns out that the location, the last one, how many are these? I should have written this down. Anyway, the last location is also active. So they get swapped and the output ends up being n.
Go back to the definition.
Yes. And I will give a picture of the particular of the definition also in a second.
Right, so like, I guess in this definition, when you say it changes if changing tx to any other value, that's does not mean that's like it changes if there's like so like you could change it to a specific different value where it does change the permutation, but that's not good enough. It has to change if you
Yeah, like if you change it, if we make any change, it changes the output. Yeah. And so let's look at another one here. This one actually is a fixed point. Here's one that has a lot of active locations. So now let's look at this definition. So for example, here this location 3 is active for pi on 3. And that's because if I change T3 from 3 to 2, then my output has changed. If I change it to 1, the output changes again. 4 is not active. That's because if I change T4 from T7 from 4 to 1, nothing happens. Or to 7, then also nothing happens. It's only if I change it to 3, which is the unique value that is like kind of the intermediate state of my computation at this point, then the output changes. So now, what do we learn from this? We learn that at least we have an intuition now that if I use this superposition version of this strictly monotone decomposition, then I have these n many registers, right? They contain kind of the superposition of these t values. And if some forward query is made on X, then it should be that the resulting state is approximately still supported in kind of a sparse subspace that has only log n many locations that are not still in the uniform superposition. Or if we use this kind of basis change unitary and change everything that's uniform still to bottom, then it kind of the sparse representation becomes more apparent. Yeah.
In your previous figure,
Yeah.
isn't the empty sets those vertices that is being hit by when you traverse from right to left?
Yes, it's basically that's another way to say it. It's all the transpositions x prime tx prime, such that if you compute the permutation using the strictly monotone decomposition on X, and your computation arrives at this transposition, then the intermediate state is either X prime or Tx prime.
Yeah.
And it can only be Tx prime except for in the case of the input. The case of X, Tx. Right. Now let's look at this idea of using the strictly monotone decomposition to create a superposition order. So we basically initialize this huge register. I'm going back to capital N equals 2 to the little n. We initialize it with all the all bottom symbol. However, I see that that's a typo. So the dx register now has state space c to the x plus 1, right? Because we added this bottom dimension. But now not all of these registers are created equal, because the first one only needs to hold t1, which is always 1. But the last one needs to hold t2 to the n. Now basically, how do we answer queries? Controlled on the input being x, we apply v. In this case, we apply v, which is like this swap between bottom and the uniform superposition on all registers. But note that now basically each register has its own version of v, because it needs to swap bottom and the superposition of x many values. Then that's just the formula. I mean, you know what the superposition is. Actually, I should have removed this. I get to talk to the less quantum audience before. Now, controlled on the database register being in state pi, and remember that pi is specified by this list of t's, right? I reply to the query, right? I XOR the value pi of x into the y register, which is the query and query output register, and then I undo v. So at this point, it's very abstract, right? And we don't yet know really what, how local the impact of this second bullet is, which is controlled on the t values specifying a permutation pi applied, right? But it turns out that it has a lot of nice properties, and some of them follow from this result on the active locations, or at least they are related to it. And the first property is the sparsity, right? After Q queries, the database is still supported in a subspace that has only order Q times n many registers that are not in the bottom state. And now this only holds up to kind of a negligible difference, because of course, I can write down a permutation whose strictly monotone decomposition has where all locations are active when computing it on the input 1. For example, the one where t1 equals 1, t2 equals 2, t2 equals 1, t3 equals 2. That basically where the input just steps up all the way. But that has these type of permutations just have negligible weight in a uniform. uniformly random permutation. Also, another good thing is after a query with input x, if the input is large compared to 1, then dx is not equal to bottom, because the position x is always active on input x. This basically is what happens. Also, it turns out that it lends itself to a progress measure based query bound technique. And yeah, that fact is definitely related to both the first 2 bullet points. That we basically have still have this sparse subspace where the state is supported on, and that we can recognize by looking at the register dx whether pi of x is known to the algorithm or not. What's a bit annoying is this condition x much larger than 1 here. But now if we basically apply this strictly monotone decomposition in a randomized order, like instead of starting with n, we apply like a random permutation and use the result in an independent random permutation and use the resulting order to apply the strictly monotone decomposition. Now, an algorithm interacting with this oracle will still be exactly indistinguishable from a random permutation oracle. In particular, from an oracle with a permutation pi, where pi is the permutation we decomposed into using the strictly monotone decomposition. So the algorithm's view will always be independent of the order that we applied the strictly monotone decomposition in.
If you randomize the order, what happens to the state spaces of all your little kind of database outputs?
We can still think of the same, like ordering the registers in the new randomized order, if we want, and then it looks the same. And the good thing is now that basically any algorithm making polynomially many queries will most likely not query a small input, and then we get rid of this problem.
I just didn't fully understand the requirement for x to be large.
So the problem is like, going back to the picture, like T3 only has 3 possible values. So the uniform superposition of these 3 values, it's not very orthogonal to the computation basis states, right?
Yes,
so that's terrible.
That's
But then for larger inputs, that's fine.
Yes.
Where were we? Here. Yes. So this is my list of nice properties where conditions apply, which is hard to neglect. Yeah. Now let's look at the progress measure based approach. I think I have a couple of minutes left. I'm supposed to talk for an hour, including questions, right? Yeah. Right. So now basically the key to query bounds from this kind of superposition oracle or from compressed oracle for functions is the ability to answer the question, did the algorithm query some x such that x and h of x is fulfill some relation, right? And the good thing is that this is the OR of the computing of the commuting measurements that answer the question, did the algorithm query a particular input x? And if so, was the pair x h of x in the relation? So now, we have these small operations, which is like basically targeted like a measurement that just measures the register dx, and it answers something about what the algorithm knows about h of x and to the properties of h of x. But the good thing is all of these measurements commute, and we can answer this existential question in the first line. Yes?
Yes, it's very classically, did the algorithm query X? But of course, in reality, it will query things in superposition, so there is not really a yes or no answer to the question. Are you really talking about how much information has been built up about HX?
Yes, and actually the good thing is the answer to this question is classical after applying the measurement. So basically, the measurement of this internal register will collapse the state to either a world where the algorithm has learned the output h of x, or a world where it hasn't.
So the internal register, that's the H part or the algorithm's part?
The h part, yeah.
Just a quick question, what is the order of commuting measurement answering the question?
Oh, I was just phrasing that, like, the first thing here is like an existential question, right? Does there exist an x such that x was queried and x and h of x fulfill the relation? And I can phrase this as kind of the OR of the outputs of the of all the kind of 2 to the n many questions in number 2, right? Now, the good thing is our new oracle that we call SPO, Superposition Permutation Oracle, it allows the analog of the number 2 here. It allows for a measurement that can answer the second question here. For a particular input, did the algorithm learn the corresponding output? And if so, did the input-output pair fulfill the relation? However, these measurements now, naturally, because the outputs are not independent, don't commute anymore. So we cannot, as far as I know, we cannot kind of just take the OR of like exponentially many of these. There's some techniques for taking the OR of 2 non-commuting measurements if they almost commute, but they don't work here. So now instead we use a different progress measure, because this projector that tests does there exist an output input-output pair that fulfills the relation. That's exactly the progress measure that facilitates query lower bounds for the random function superposition oracle. So now instead of using this existential projector, we define this particular procedure that answers the question: did the algorithm query x, and if yes, was x and pi of x iteration for a uniformly random input x. So now we use this as a progress measure and try to give an extremely small bound on the probability that the answer will be yes. And in the end, we conclude that if that extremely small bound holds, then for a given x, there still needs to be a reasonably small bound that holds, right? Basically by this pigeonhole principle. If I have like an expectation over this randomly chosen x, I will only find that the corresponding input-output pair was learned by the algorithm and is in the relation with probability 1 over 2 to the 2n, let's say, then I can still conclude that it can be at most 1 over 2 to the n for a given. So that's the strategy. And for this, we would define this operator. The first, the part on the right is basically this projector that projects away from what I used to call the bottom state. We kind of omitted this basis change, but for the presentation, I found it nicer. So here it projects away from the uniform superposition, which represents the state where the algorithm hasn't learned this t value. And then there's the second projector, which just projects onto all out of the subspace of permutations where the input-output pair x pi of x fulfills the relation. And now basically, if picking x at random and then applying this operator and taking the norm of this, that's our progress measure. Yeah?
Good question. Well, what is the issue of just measuring all the t's?
We can measure all the t's. That's okay.
And then look at it as like a database or something.
And there's like an extremely annoying problem that arises in that case. So maybe let me quickly finish the talk. It's almost finished, and then if you want, I can explain it. So here's a lemma, and it looks scary. Let's not look at the details too much. But it's this progress measure lemma, right? Like on the left hand side, you have a difference between just applying our E operator to a state and first applying the query operator and then the E operator. So that's kind of the progress that we want to bound. And then we get some bound. And the only thing I want to point out is that, for example, this term here, for a random x, it has order 1/n squared. So that's exactly the scaling that we need to be able to still get a meaningful bound after this pigeonhole, the principal argument. Some other term, for example, this one, for a random x, because of the sparsity, that norm expression will be small, like order 1/n, maybe log n/n or something. And this first expression here is also small. Yes?
How do you capture the inverse queries? Like is for instance, your Oracle state, are there kind of like two databases that are heavily entangled with each other, or?
No, the inverse, that's right, I kind of brushed them under the carpet, but they answered exactly in the same way. Like apply this uncompressed unitary, then answer the inverse query by using the information in the database, the T values, yeah, and then recompress. And analyzing the inverse query is more annoying because there's no particular input, no particular T value that is always active for inverse queries. Right. Let me maybe skip that. So now we get this generic query bound, and that's maybe what I should almost conclude with, where we have the probability that some algorithm interacting with the random permutation oracle and its inverse oracle outputs an input-output pair, also an input, so that this input with its corresponding output under the permutation fulfills a certain relation. That's bounded by some polynomial in the number of queries times log n/n. So that's kind of our main result.
Is it a q cubed instead of a q squared because you can't use the progress measure that you want?
It's q cubed instead of q squared because the proof is terrible and I don't exactly know where the loss is. I think I have a candidate where this loss happens, but I don't know how to get rid of it. I don't think it's that it's basically, maybe you can say that you can use your explanation also, yeah. Okay.
Do you think it's an artifact of a proof and should actually be q squared? Or?
Yes.
Okay.
It should be q squared. And then we can apply this, for example, because we only can deal with one input-output pair at this point, we can look at the one-round sponge, which is this construction of a function that maps x to y. So take x, append some zeros, apply a permutation, then get rid of the last half and output the first half, let's say. And we can just straightforward apply our generic result to get a bound for pre-image finding for a one-round sponge.
But you can't handle multi-round sponge.
No, at this point we can't. And there's actually a much better result for one round sponge that doesn't have the non-tightness. But unfortunately, the proof of that result doesn't suggest a generalization to more than one round. Actually, our techniques should be fit for proving constant round sponge. But we didn't want to deal with the clutter for this small prize, because what we actually want is polynomial. Okay, so in summary, we now have a superposition oracle for permutations that's at least fit for proving some query bounds. And as an application, we get this pre-image resistance for one-round sponge, which, by the way, this other work is concurrent. It was open until now, right? That's really surprising. That this extremely simple question about this construction that uses makes one query to a random permutation was open. Great, yeah, thanks for your attention.